Oh, hi there.
Oh, hey.
Hi. Thanks for showing up for your learning. I know it's been a lot of math already. That's great. Our brains are primed and just churning and ready for the new knowledge to be put into our mind machines and chewed up and digested into new knowledge. When we're thinking about exponential functions, the basic ones are simple growth and decay problems. Exponentials don't create lines the way, something like I make $15 an hour, I work this many hours. The number of hours I work or the amount of money I have does not influence my future income. The rate of income stays constant. Those are lines. With something like I have $100 in the bank, every year it grows by 10%. There, the 10% is multiplying itself every year. The amount of money that's accumulating is increasing the growth. This is why it creates a curve that grows in that manner. Or similarly, if you're losing 10% of your money every year, it's going to create a curve that decays. So growth and decay are just two different sides of the same phenomenon. And we're going to look at the other side of the phenomenon today. And these decay problems always have this type of shape that you see here. And the function is going to be decreasing rapidly in the beginning and then slow down its rate of decreasing over time. And it decreases its growth factor here. This is the B number that it's referring to here, is somewhere between 0 and 1. And these are exponential decay problems. Well, let's take a look. So we have the same function here, the same type of equation as we had for exponential growth yesterday. The only difference is this B number here is going to be 1 minus the rate of change. So if you, say, had $100, that would be your initial value here. Call that an A. I don't know why we have P there. This is an A. And then you have your growth factor, B. Let's say we are losing 10% per year of our money. Then you would construct this B number by saying B is equal to 100% of my money minus the change. 10% as a decimal. So B in this case would be 0.9. Whenever this number is less than 1 but bigger than 0, you have exponential decay. You have an equation that will look like this. It will approach 0 but never quite get to 0, and it will be decreasing more in the beginning and less as it goes along. Carry on. Let's go. So here we are. Here are a couple equations that we would like to analyze in a table. In both cases, the initial value is going to be given by here. Just to remind you, this is y is equal to a multiplied by b raised to the power t. And b is equal to either 1 plus the rate of change or 1 minus the rate of change. So let's take a look. Here, the initial value is clearly 20. The growth factor B is 0.87. We would know that that's a decrease because it is less than 100%. It's a decrease of 13%. If I take 13% and I start with 100% and I subtract 13%, I'll end up with 87%. So there you have it, 0.87. After 1 year, there would be 87% of that initial 20. About 17, a little bit higher than 17. And then the next year, it's going to lose a little bit less than 3, and then it's going to lose a little bit less than 3, and the amount it's losing is going to be going down as we go forward. This is decay. I know this will create a decay equation because this number is less than 1 but bigger than 0. This one here, this is growth. This is what we looked at yesterday. Its initial value is 54. Its growth factor is 1.05. Its percent increase or decrease, it's an increase of 5%. And this is an example of growth. Carry on. So Let's take a look at a situation. These poor bunnies. In 2005, there's 85 of them in Central Park. Not a lot for bunnies. And the population is decreasing by 12% every year. Perhaps there's a new park they opened up across town, and the bunnies are emigrating. So let's see. How many rabbits were in Central Park in 2015? So we want to know, well, let's take a look. First, we want to find our A, which is our initial value. And I see that in the question here is 85. And then I want my B, which is my growth factor. It's going to be 1 minus the rate of change. Here's the rate of change here. R equals 12%, which would equal 0.12. So I can improve this equation for B and actually find the value. It's 1 minus 0.12. It's equal to 0.88. So I'm going to use that number in my equation. I'm going to use this number in my equation. Maybe I circle them so I know that they're very significant. So I can now create a function. The population of bunnies is a function of time, and it's equal to the initial value multiplied by the growth factor raised to the power time. Every year, we're going to multiply by that growth factor to reduce the number of bunnies. So, what time are we interested in? Well, we started in 2005, and we're interested in after 10 years in 2015, how many bunnies will there be? So I do a little bit of math. T is equal to 2015 minus 2005. That gives me 10 years is what I'm interested in. How much does the population go down in 10 years? So let's input T as 10. So I would have P at 10 is equal to 85 raised to the power, 0.88 raised to the power 10. And then we get out a calculator. And we do that on a calculator. My goodness, you need a calculator. So, 0.88 raised to the power 10. Do the exponent first. We have, there will be 28% roughly of the total bunnies after 10 years. Multiply this by the initial amount. There we go. There will be 24 bunnies, give or take. This is a predictive model. You don't need to worry about the fractional bunnies, just round. 24 bunnies. So then we'll finish with, therefore, there will be 24 bunnies. Or I suppose we should say there were, because this is actually we're in 2022 now. But this is not an English class. I can use the wrong tense if I want. Maybe I have a time machine. Who are you to tell me what's correct? There will be 24 bunnies in 2015. Done. Sorry?
Oh, that's true.
Isn't that a little bit like... No?
It's the same thing as negative and positive. It's so similar, but it's wrong.
Okay. Well, then I lose all the marks here. Mr. J equals 0%. Sad. Don't worry, I'll try and have a growth mindset about it. Let's keep going. We can also solve for t. So the other type of problem that we're going to be giving you is how long will it take for the population to fall to a given level or for the money to fall to a given level? And we can solve for t with either guess and check or graphing. Let's take a look. So go through and read. A city finds that its residents are moving to the suburbs at a rate of 4% per year. So there is our R equals 0.04. That's 4% as a decimal. Given that the original population was 1 million, so the population at 0 is equal to 1 million. That's the initial value. That's a comma that came out as a period. So let's do that there. And then how long will it take to for the population to decline to half of its initial amount? This is our P at 0. This is our, why did I call it P at 0? This is just A. That's the initial amount. How long will it take for it to decline to half of its initial amount? Well, there's a couple ways to do this. we could say that we want P at T, and we're going to be solving for T. We're going to solve for the amount of time that it takes for the population to become 500,000. We could do it this way. Or you could simply find when does 0.96 raised to the power T equal 0.5. If you can see that that's a quicker road to a solution, take the shortcut. I'm not going to take the shortcut here. So let's take a look. I would set this up. Oh, well, we also need our B. So our B is based on our R. Our growth factor is B equals 1 minus 0.04, and that's equal to 0.96. That's our growth factor. That's our initial amount. Let's go. So P at T equals 1 million multiplied by 0.96, that's exponential decay, raised to the power T. And I want to find a solution to this equation. 500,000 equals 1,000. Sorry, 1 million multiplied by 0.96 raised to some value T. I'm going to find the value T. So then we go ahead and divide by 1 million. That's a lot of zeros. Divide by 1 million. You'll notice that 500,000 divided by a million reduces to 1/2. So do that. Equals 0.96 raised to the power T. And now we guess and check. So set up a table for guess and check. If people have it already, that's great. Hold on to it. I want to guess and check. I don't have the answer handy. I'm going to show you what it looks like when I guess and check. So I put it in here. My target is 0.5. I might circle that there. And I might say, let's try 10. And I do this. And I put in 0.96. And I raise it to the power 10. And I know this is going to be a little bit too little, but it's pretty close, actually. 0.66. All right, I need bigger. Let's try 15. 0.96 raised to the power 15 equals, oh, I'm getting closer. 15 gave me 0.54. It looks like maybe 16 is the answer. Let's try 16. 0.96 raised to the power 16 equals, oh, 0.52. We're getting closer, but we're not there yet. 0.52. I look up here. How long will it take for the population to decline? Well, how many years, let's say? We want it to the 1 year. So I think it's going to be within that 16th year. Let's see if 17 goes past. 0.96 raised to the power 17 equals, it's now below. So 17 is so very, very close. It's 0.499, blah, blah, blah. It happens just before the calendar turns to the 17th year, just at the end of the 16th year. Probably something like 16.95. Really, really high decimal place. But that's still within that year. If it happened on December 30th of this year, we would still say it happened in 2022. We wouldn't round up to 2023. See what I mean? So it happens within 16 years. So therefore, it will take 16 years and 11 months and some days to do that.
Could we write like just?
What's that? No, I choose values of t to substitute into this equation and use my calculator to evaluate them. And then the outputs of my calculator, I want that to target 0.5. And I choose different values until I get close to 0.5. And then I'm satisfied once I get within one decimal place, unless the question asks me from any decimal places.
Could we just write just less than 17 years?
If you wrote just less than 17 years, it shows me that you have a good understanding of this problem. So let's take a look at it in Desmos. All right. What I wanted to know was if y is equal to 0.96 raised to the power x, okay, when does that equal 9.96? 0.96, thank you. When does that equal 1/2? So y equals 0.5, okay? And we go ahead and we find the intersection here. There it is. It's a 16.98. So just like we predicted, just before the calendar turns over to the new year in the 16th year. And that's graphically solving it. Notice I don't really need to put in a million and have it be equal to 500,000. I can just put in the thing that we algebraically simplified. If I did it the other way, I just have to change the scale a little bit so I can see my solution. And it still works out. So let's go back here. So then my wording, so Oscar's is fine. So we might say, Oscar's is just lovely. Therefore, we might say, therefore, it takes almost 17 years for the population to be halved. There. Okay. One more idea. Another common decay type problem that you will have is the half-life of radioactive materials or the half-life of drugs in the human body. So a drug might decay exponentially in the human body. Initially, when you take the drug, it gets absorbed very quickly and then starts to decay exponentially. So losing perhaps half of the concentration in the body every 4 hours. And never really disappearing completely, but really tapering off towards zero and approaching zero. So half-life is something that shows up in a lot of disciplines, and it's an example of exponential decay. In these cases, you are given the amount of time that it takes for something to be reduced by half. And the way you can put that into an equation here is you can have the amount at time t is equal to the p, which is the principal. I would just have a there. You could have a little a, the initial amount. And then here your growth factor is 1/2. Your exponent, just set it up as with a k transformation, your exponent time divided by the half-life. And you will find that this trick creates some very elegant equations that are easy to work with and easy to model half-life situations. Okay. The P or the A there, that's just a stylistic thing. I prefer A. We had A in the other presentation. I don't know why the person who created these presentations changed the value. Okay, let's take a look. Radium has a half-life of 1,620 years. How many grams of radium will remain after that many years? Well, this is how you answer this type of question. My A, my initial value is 50 grams. My B, my growth factor is 0.5 or 1/2 because we're talking half-life here. And the H is the half-life of the substance is 1620. So there are the numbers that we have. If we want to know in this amount of time, T, we're going to be evaluating at 4,860. This is how we set up our equations. The amount of this substance at time t is going to be equal to the initial amount multiplied by the growth factor raised to the power t divided by the half-life 1620. We have been asked to find the amount at time 4860, and that would be 50 multiplied by 0.5 raised to the power 4860 divided by 1620. Aha! 48260 divided by 1620 is 3. So we need to apply the half-life 3 times. Basically, divide 50 by 2 3 times. So it's 50 over 8.
I didn't know there was a half-life 3.
Huh?
I didn't know half-life 3 was there.
No, the half-life is not 3. The half-life is 1,620 years. 4,860 years happens to be 3 of those. So when I evaluate that, your calculator will tell you that that number is 3. Or you know that 16 times 3 is 48, and 20 times 3 is 60. And so then you can do it in your head.
Well, half-life 3 is confirmed.
Sorry?
The game Half-Life.
Oh, Half-Life 3 is coming out soon? Oh, cool. Yeah, cool. All right, so there are 3 half-lives here. Oh, I see. That's a good one. So we are going to have 3 half-lives here. This answer is going to be 50 times 0.5 raised to the power 3. Let's just solve that exponent. And then 0.5 to the 3, well, if you know that that's 1 over 8, fantastic. If you don't know, your calculator will tell you the answer. So we would do 50 multiplied by 0.5 raised to the power 3 equals 6.25. So there will be 6.25 grams of this substance left after 4,860 years. Yeah. Okay. So that is the new ideas. Hooray! And any questions, hit me up by email. Bye for now.